You are given two strings, a needle and a haystack. So we want to find the needle inside the haystack. What that means is needle is our pattern string and haystack is our target string. And if you can find the needle within the haystack, you return the index. In this case, because this is a pattern, so you return index 0, 1, 2. If the pattern cannot be found, you return -1. In this question, we're going to use the Kmp algorithm. Before we talk about Kmp, let's think of what to do in a naive method. You have two pointers, one pointer for target and one pointer for pattern. What I'm interested in is what to do when it comes to the current index. So let's say the current index for target is I and current index for pattern is j. And we have already matched the pattern prior to j, which means this and this is the same. So when it comes to matching I and j, if they're the same, then the problem is trivial, right? Because we're just advanced in index. I advanced, j advanced, so that's trivial. So when they're not the same, in a naive method, you will backtrack I and make I go to here. Since the character at I and j are not matching, which means this substring is not matching, so we need to start all over again and start from here. So you realize that's a lot of wasted work. That's why naive method is very slow. What Kmp does is that you will never move back the target string index. So you will never move back I. The Kmp algorithm has two steps. Build the longest prefix equal to suffix table, then is the main algorithm. The Lps table is always related to the pattern. It has nothing to do with the target. So let's say you have a pattern string that looks like this. The Lps table is an array of equal length. Inside the array is going to store integers. What that integer represents, I put the definition here. I know it's a mouthful, but let's go through this together. It's the longest prefix length that's equal to suffix inside the substring from index 0 to myself. So let's just break this down. Let's say I am at this current index. Now, what is the substring from 0 to myself? It is ADCA, right? Now, what is a prefix? Prefix is actually A, AD, ADC. Now, ADCA is not a prefix because we don't consider the string itself to be a prefix. Now, what is a suffix? Suffix is A, CA, and DCA. Similarly, the string itself is not a suffix. So what is the longest prefix that's equal to suffix? In this case, it's A equals to A. So the longest prefix equal to suffix is 1, right? Now, AD is not equal to CA, right? So it's not 2. So in this case, the value is 1. Now let's look at a different index. Let's say we are at this index, D. What is the substring? The substring is ADCAD, right? What is the longest prefix length that's equal to suffix? AD equals to AD. Okay, so we have 2. What about ADC? Well, it's not CAD, so it's not 3. So in this case, it is 2. By similar logic, we can fill up the entire table 0, 0, 0, 1, 2, 0, 0. Let's look at a different pattern string, and the interesting index is this index. So what is the substring? This is the substring. What is the longest prefix is equals to suffix? Is this 3? No, because AAB is not AAA. Now, is it 2? Yes, because AA equals to AA. So we have 2 here. By similar logic, you have 0, 1, 0, 1, 2, 2, and 0. Now you may be wondering, why does this LPS table matter? Why does it make it such that we don't have to move back the target string index? It doesn't give us any intuition, right? I gotcha. That's why I'm not going to tell you how to build this LPS table right now. Instead, we're going to jump straight to the second step. Let's pretend that we already know how to build this LPS table and see how does the main algorithm works. So now let's look at the main algorithm. We are currently at index I in the target and index j in pattern. The assumption being we have already matched the pattern prior to j, so this matches this. Now the trivial case is when the character I matches j. So that's trivial, so we won't talk about that. We will talk about what happens when they don't match. And the magic of Kmp is that you do not need to move back I. So now we'll see why. Since we have already built an LPS table in step 1, we know that this cell stores the longest prefix that's equals to suffix. What that means is this prefix and this suffix is the same. And similarly, this prefix and this suffix is the same. Why? Because we already matched these two substrings. Okay, so can you see whether you can make use of this piece of information? And if you cannot, let me remove some brackets to remove some distractions. Hopefully this is clearer now. When I and j do not match, we no longer need to move back I. The reason is we already know there's this part, this red part of the substring that already matched. So I can just sit here and instead we will move j back and move j back to here. And that's much cheaper than moving back I. So the question is, what is this index that j should move into? That number is actually the value here because that value is the length of this prefix. And the number plus 1 is the index. So the number is LPS j minus 1. Again, just to reiterate, when j and I do not match, we do not need to move back I. Instead, I can just sit here and instead we move j. So that's cheap. And we can finish the target string in one pass. Because we have a j minus 1 in the formula, that brings the question, what happens when j is 0? When j is 0, we are at the beginning of the pattern, and the beginning of the pattern is not the same as I, so we need to advance I. Now we can actually start coding the second part of this algorithm. I will come back to the first part later, so let's build the LPS. But for now, let's just pretend that we already know how the LPS will look like. We iterate over the target string and we need to maintain an index for the pattern. So j is index for the pattern. I is the index for our target. Now, if they match, that's kind of a trivial case. You will advance both the index. You will find a complete match when the index for j is out of bound. Once we found a match, we need to return the starting index of the match. Now, I is the ending index, so you shouldn't return I. Instead, you should return I minus needle.length. And do bear in mind, we are doing this after I has been incremented. Else, we will assign j to LPS j minus 1. but it's only valid if j has some sort of value. So we need to check whether j is greater than 0, else plus I. We can move in one line. And now we are ready to move on to the first step, which is building the LPS table. So now let's look at how do we build the LPS table. Let's investigate what happens when this is our current index. I is the notation to represent the ending suffix. When I am at I, it means I am inheriting an existing matching suffix and a prefix. Because the fact that I am at I, it means I have already calculated all the values prior. And I know what is the current matching longest suffix and prefix. So I am inheriting this fact. So I want to compare whether I matches this j, which represents the ending index of the prefix. If the character at I and j are the same, then that's a trivial case. We can just advance I and j. But what happens when I and j are not the same? It's not obvious what value should we assign here. Now we can actually make uses of the value at j minus 1. Now what this cell represents is the longest prefix matching suffix of this substring, which means we know there's a prefix here and suffix here that matches. By the same token, because these two red strings matches, we know these 4 blue substrings are the same. And let me remove some distractions to make it clearer. Hopefully this is clearer now. We know this substring and this substring is the same. So we can make use of the fact that these two blue substrings are the same and compare this character against I instead. If this character and I matches, then we know what to put here. We know the length will be this length. But if it is not the same, we need to keep shrinking the prefix suffix zone and keep setting back j. And this is a recursive process. Let's step back for a second and see what we did. Initially, we are at I, and we are writing off of the fact that there is this red area that's the matching prefix and a suffix. So we are comparing I and j. Unfortunately, I and j do not match. Then we say, okay, we are probably being too greedy with our search zone, so let's reduce our search zone. So how do we do that? It's by setting back j to this index. And that gives us the next best thing, which is this matching blue zone. So we need to compare this character with I. Unfortunately, it also does not match. Then we just keep doing this in a recursive way. But in the actual code, you will not write a recursive code. We will see later why. So we are now ready to code the first part, which is building the LPS. We will iterate over the needle. We will start from index 1 because at index 0, the prefix and suffix is the same as the substring itself, and we don't consider that a prefix and suffix, so it's not a valid case. And I means the index of the suffix ending index. And for j, we will use it for the prefix ending index. Now, if it is matching, if the suffix and the prefix is matching, that's kind of a trivial case. Or rather, well, we need to set the LPS value. I am post incrementing I here because I need to be incremented later. I am pre-incrementing j here is because I want to know the length, and the length is actually 1 plus the index. That's why I pre-incremented here. If it's not the same, then you will set back j. Now obviously j, we need to do a check on j. Else plus I. Well, it is actually very similar to the second part. Oh, I shouldn't increment it here. And there we go.